Alright, welcome back to the session. Right? Well, last time we had discussed about the multiplication rule and the conditional probability. Well, let's see some other examples. I say, well, the X data DVDs in a lot of 50 have a defective rate of 0.5%. In other words, the 0.5% is 0.005 of one disk to be defective, the likelihood, right? 0.005. We're asking for, well, what is the probability that in a lot of 50 DVDs there is at least one defective? 0.005 for one disk to be defective and asking for at least one defective. I recall back of what we had done for the last time, right? The boys or girls coming out. Well, this one looks very similar. Right, if you go back to last time's lecture, it is actually asking for the similar thing. Right, the probability of at least one defective out of 50, right, is actually the complement of all good. Is the complement of all 50 DVDs are good ones, then what we can do is by the, like what we said, the opposite or the complement probability, to find it as 1 minus the probability of all 50 are good. All 50 are good, which means the first is good, second is good, all the way to the 50s are good. That is the probability, right? But each individual are not like so affect to each other. In other words, we'll see soon is called independent to each other, right? The first one is defective, doesn't affect the others, or anyone is defective doesn't affect the others to be all good or defective. So the 50s are good, which means the first is good and the second is good all the way to the 50s. Right, the 50th, all 50 of them are good. But what we find the probability of a DVD is good, that is the opposite of it is defective. The probability of good here is 1 minus the probability of it to be defective. Of course, if it's not defective, then that's good. I'll have 0.005 or 0.5% of one DVD to be defective. Then if that is good, that will be 0.995. Right? Or if you want to see that is 1 minus 0.005 is 0.995. Right, then we use the calculator to find it out. 0.778. If you use a calculator, you could verify that 0.77 something. Right, then 0.0778 will be the likelihood, and when we subtract that 0.222. Right, so that is the likelihood, about 22% that we get is at least one defective, so maybe 1 out of 5 boxes of the DVD will get at least one to be defective. That is the likelihood of at least one defective of a lot of 50 dBs. Only not only, it is 0.222. Right, the next question you can see on your notes. In this case, we're on page 34 on the notes. Well, that is asking for similarity. Given that the probability of a certain calculator functions is 0.97, like when you're doing during a test or doing something calculation, right? Some button maybe works, some button maybe not. If one button doesn't work, you cannot say the entire calculator is working, right? Then you cannot just say it's not functioning well. Then the probability, of course, will be very high to be a calculated function. But you don't want to have some risk, right? For a certain exam, you do not even want the 0.03 likelihood to have your calculator you bring to you is not working. Right? So to avoid that case or minimize that case to be happen, what we could try to do is bring another calculator. Right, so you want to minimize that likelihood of you don't have calculator. You want to bring two of the calculators to an exam and try to ask, well, what is the case that they are both not working? Why they both not work? And also asking for, well, what is the likelihood that, well, at least one functions? Or if at least one functions, then you will conquer at least the exam by the supply part. You at least have the calculator with you, right? So which can solve some of the problems. Right, so let's see. Both not work, which means the first one is not work, the second one is not work. Right? We have the function, or have the probability it functions is 0.97. Of it does not work, that is 0.03, right? Because the complement of working is not work. We have the first isn't work and the second isn't work. These two coming from the two calculators, right? The first is not and the second is not, that can multiply together, which is 0.0009, right? Which is less than 0.09%. I mean, it's less than 0.1%. It's 0.0009 exactly, right? And the part B, this one is working. That is just simply asking the probability of at least one work. Right? At least one works means if you separate in cases, intuitively the first works, second not, or the first is not working, second calculators work, or both of our calculators function well. Right? Three cases. But if we do the complement, that will be 1 minus the case that they both not work. Well, 1 minus the excluding the case of both of them are not work, that is the case, or those are the cases of at least one of our calculator you bring is working, right? And we'll subtract from 1, that is 0.9991. It is step-by-step analyzing, and we get the result of at least one of it could be working is more than 99%, 99.91%. Compared to 0.97, even though 0.97 is already large, but so we have 3% of the likelihood what the calculator will bring us is not working, and the thing is we do not want it to be under risk, right? And simply by bringing an extra calculator will increase the result or increase the likelihood to be 99.9%, more than that, right? So that is simply what we have. So again, how can we multiply the 0.03 together, right? The 0.03s together like we just erased this, because our first calculator, if it's working or not, doesn't affect our second calculator if it's working or not. And that is called independent. Right, the independent events. Well, it seems like in general like what we can see, the probability of B, or if it has the condition, this seems like very rare. Right? In general, they are not equal. we have a simple probability of B event, right? But if we have an extra condition of A, then the probability of B given A occurs is not equal to the probability of B itself. But in some case, the probability of B simply just equal to the probability of B given A. Right, those couple cases could be happen that A gives no information about B. Right, that's our first case. It could be like what we had before, the first calculator and second calculator. Or if the second calculator we can know does not affected by the first calculator's situation. They are not dependent. In other words, they are independent. Or other case, the other case is that, well, it actually gives the new information about B, but that new information does not update the likelihood of B. So we can see that actually mathematically, right? The conditional probability equals to, well, the conditional probability in formula that equals to probability A intersection B over the probability of condition. Right, that's the formula of conditional probability we had discussed last time. And if independent, that intuitively the probability of B given A should equal to the probability of B. Right, should equal to the probability of B. Therefore, we take this part. Well, we can figure out that, well, there is a way we can determine if the A and B events are independent, right, by just determining the intersection to see if that intersection of A and B has a likelihood equal to the probability of A times probability of B. Right, so if we have this equation holds, then the events are independent. Right, if this holds, then we get independent. Right, so we get the definition part. independent events means A and B are not affected to each other. Of course, you can check by the conditional probability, but for most of the case, it will be easier to check with this formula. Right? If probability of intersection equals to their probability of each event multiplied together, right? The product of each event's probability. That is the way we can check if A and B are independent events or not. Right? Before, we had checked about mutually exclusive events. Right? A and B are mutually exclusive if the intersection equals 0. Right? Here now, the A and B are independent if the intersection equals the products of each individual. Right, so that is the way. So let's see by example, right? Right, the probability of A is 0.2, of B is 0.5, and the union has a probability of 0.7. Asking for two things asking for. Are A and B mutually exclusive? And the second question asking, are they independent? Right, for both of them, they're still looking for is the intersection. Right? If the intersection is 0, we have mutually exclusive events. If the intersection is the product of each individual, then we have the independent events. And so we check. We're given is the individual events probability and the union, right? Last time, or maybe before, I had figured out the intersection or something called addition rule. Right? If you still remember the addition rule, right? That's the union could be writing as the sum and take away by the intersection. Right? Union has a likelihood of the sum of each individual minus the intersection. And if you still remember, I have said that the position of the union and the intersection could be switched. So if we're given the two events and the union, then you could be also figuring out the intersection in this way. And that is algebraically correct. I just move the left to the right, move right to the left, switch sign, then we get the equivalent format by finding the intersection, by the way, of given the union, and of course individual. So in our question here, we given 0.2, 0.5 for each one and minus the 0.7, we actually get the intersection is 0. Right, so to find the mutually exclusive, right, the first question for the mutually exclusive, we have the intersection equals 0. Well, when the intersection equals 0, then we say therefore are mutually exclusive, right? And B are mutually exclusive. In other words, they are disjoint. Right. And check for the independent. We need to check another thing, right? We get the intersection equal to 0. What about the product? Right? When the formula tells us if the intersection equal to the product, then they are independent. But we don't know here. Right? So we need to check the product of each probability. Right, apparently not that equal to 0. That when you multiply 0.2 times 0.5, that is 0.1. It's like a half of 0.2, right? It's 0.1. So what we get is the intersection is not equal to the product. Not equal to the product, therefore A and B are not independent. Right? That's what we find based on the definitions of mutually exclusive and independent, of course using the formula of addition rule. Right, regarding to the next question, we can see similar thing. The probability of A is 0.6, probability of B is 0.4. Right, I have on my notes using different notation, so just change a bit. But anyhow, that's it. On my notes I have E and F, here I use A, B, that's same. Right? 0.6, 0.4, and the union is 0.86. And asking for are they mutually exclusive, are they independent, similar thing, we had. Right, so, resume back, the probability of A, that's 0.6, B is 0.4, minus the 0.76. Right, if you use a calculator, that's 1 minus 0.76 is 0.24. Right, hence clearly that they A and B are not mutually exclusive. Right, so probability of the intersection is not equal to 0. Hence A and B Since the intersection is not equal to 0, hence A and B are not mutually exclusive. Right, then what about independent? Independent, we need to check the products. Right, the products of A's probability and the B's probability, 0.6, 0.4, 0.24. Well, which we can see well from here, the product is same as the intersection. Right, so we can see from here that the product is equal to the intersection, therefore the events A and B are independent. Right, therefore independent. Right, that's most part of probability. Right? We had seen how to find each individual probability given situations, like about the coins, the dice, the cards, and so on, other things. Given table, and here is about the mutually exclusive or independent. Even the addition rule could be transformed into other cases, like here, or we can find intersection given the information. Right? From that, we can check if the events are disjoint. Also, if we can check if the events are independent. Right? That's the majority part of the probability. Then we move on to the next section of counting. Please go. Right, if you still have the outcome of the dice or the cards, right? We have 4 suits of cards with 13 kinds of each. Then we know that 4 times 13 will have 52 cards. And rolling 2 dice, we know that when we have the first roll is from 1 to 6, the second die could be also have Lansdowne value from 1 to 6, then if we count simply, that will give us 36, and that 36 is also 6 times 6 of each die's outcome. Right, so which means it's depending on the product. That is the fundamental counting rule. Experiment 1 has m outcomes, experiment 2 has n outcomes. Then the total number of outcomes is n times n. Right, so like the rolling dice, right? The first die has 6 outcomes from 1 to 6. The second die also have 6 possible land value from 1 to 6. Then the total number, if you count simply, that's 36. If you multiply using this fundamental rule, that is 6 times 6. Right, so here, if we list the first experiment has the first outcome, second experiment varies for n different subjects, for n different outcomes for the total event. And then also the first experiment can vary also. Which we have n columns or n objects or n outcomes of each row. Right, then we continue the listing of rows. That we're gonna have is m different rows. 1, 2, 3, 4, all the way to the mth outcome of the first experiment. Then each row will have n different outcomes regarding to the second experiment result is varying. Then total there is m times n. Right? That is how the outcomes being listed. Well, that is the specific most fundamental case, and we're going to see the example. Henry has 5 shirts and 3 ties to match the shirts. How many ways of a set of a shirt and a tie? So 5 different shirts. Well, intuitively, right? Each shirt can have a tie to match it, and each shirt has 3 different ties can matching it, and we have 5 ties. That means for all the 5 ties, they have 3 shirts to match in each one, right? And that combination or that set under each combination is different, right? But when we have seen the fundamental rule of counting, that we can know that the way will be just 5 shirts times 3 times for each shirt that matching. That is total 15. Different set, which means Henry will look totally different in 3 weeks, assuming he works 5 days a week, right? He will be totally looking different in 3 weeks. Then after that, that may be another round, right? But that's shirts and ties, right? Could be the counting rule could be extended to general, maybe not only 2 experiments we have, maybe more than 2 experiments. So we have the general case. Oh, for something like if Henry wants to look different, right? What about not only the shirts and ties, right? What about the pants, what about the shoes? right? So it could looking differently. Well, let's move on to the next example. Well, a committee in a college, it looks so separated. A committee in such a college has 3 freshmen, 4 sophomores, 5 juniors, and 2 seniors. I want to form a subcommittee. Well, how many different subcommittee with one of each category are possible? Right, so before fundamental, we're just saying, well, first and the second experiment, like to just shirt and tie. But when we extend it more, right, each freshman can choose, the freshman can choose from the 3 people, the sophomore can choose from the 4 people, right, we want to each category 1 person, and the junior can be selected from 5, and the senior can be selected from 2. Right, so when we select that each one is being selected and each one has formed in different ways, it's just like extending our experiment to 1, 2, 3, 4, all the way to maybe k different experiments. Right, but now here we have 4 categories considered as 4 experiments, which each experiment has different varying of number of outcomes. Right, 3 outcomes from freshmen, 4 outcomes from sophomores, and so on. Right, so when we want to choose a subcommittee, 1 each, we just have 3 ways to choose the sophomore. 3 ways to choose the freshman, 4 ways to choose the sophomore, 5 ways to choose the junior, and 2 different ways to select the 2 senior from to get 1 person out. Right, that in total and multiply is 120 different committees it can form.